Welcome back to the series of lectures on basic physical chemistry at the Department of Chemistry, University of Lagos. In this video, we'll be talking about thermochemistry. Mostly it's an introduction to thermochemistry. The thermochemistry studies the energy changes in form of heat taking place during chemical reactions. The chemical reaction can be carried out under constant volume, in which case we'll be measuring the internal energy, since the heat changes at constant volume is the internal energy, provided no other form of work takes place again. Or we can also measure it at constant pressure, which is commonplace in chemistry, and in such situation we will measure the enthalpy. If we consider a reaction going from reactants to products, the change in enthalpy, because this is a process, will be the sum of all the internal energies of the product minus sum of all the internal energy of the reactants and that of the products. And that change in enthalpy is also as given sum of the enthalpy of the products minus sum of the enthalpy of the reactants. And this is because both enthalpy and internal energy are state properties. They do not depend on how the state was achieved, rather on the state. The delta H is called the heat of reaction or enthalpy change, and it's often recorded under a set of standard conditions. In chemistry, a standard condition is when the reactants and products are in their standard state. And so once this is reported, we say that delta H standard, the naught stands for standard, and then delta U standard, we are reporting the change in internal energy. Let's recall U is internal energy, H is enthalpy. And the standard state of any substance is a state at a specified temperature. So we can talk about temperature 100 degrees or 0 degrees. So it's its pure form at 1 bar. 1 bar is slightly lower than an atmosphere. It's almost. So at 1 bar, which is almost the standard pressure in which most reactions take place. So we can have water at H2 at minus 10 degrees. That standard state is ice. So the temperature is being specified at 1 bar. And at 10 degrees, it's a liquid water at 1 bar. So enthalpy changes. The sign of enthalpy is very crucial. If delta H is negative, then the reaction is said to be exothermic. Delta H negative means that the energy of the product is higher than the energy of the reactant. It's a usually desired reaction when you're looking for reactions that would give energy. Energy is desired in all areas of life. If delta H is positive, we say it's an endothermic reaction. An example of an endothermic reaction is water freezing, water vaporizing, water liquid going to the gaseous state. So you add energy to the system. An example of an exothermic reaction is calcium sulfide burning in oxygen, and it gives us energy. So reactions like this, where delta H in standard state, that's because all these are given in standard state. Reactions such as this are called thermochemical equations because the delta H, as change in enthalpy of the reaction, is provided. So this is a exothermic energy goes to the surrounding. Endothermic energy is absorbed from the surroundings. Whatever the case may be, this is moving more than me. Whatever the case may be, the going to the reactant product always requires a barrier called the transition state. Okay, so that's in the field of kinetics. So this is an endothermic reaction. The products are higher in energy than the reactants. This is a exothermic reactant. The products are lower in energy than the reactant, and this is like a potential energy surface or a reaction pathway. The graph. So these are other examples of thermochemical equations. We can write the delta H outside the equation, or we can write the heat released as part of the equation of reaction. And in this case, for an exothermic reaction, it is written at the product side. If we look at it from the endothermic point of view, it's considered, the heat is consumed, which means it's considered part of the reactants. Enthalpies are often labeled by what they represent. For example, the enthalpy of combustion for a combustion reaction, enthalpy of hydrogenation for an hydrogenation reaction. So enthalpies are labeled based on the nature of reaction. So whatever the name of the reaction is, so enthalpy of dissolution or solution, so that's enthalpy change when 1 mole of substance is completely dissolved in infinite dilution. So if you notice, these enthalpies are given in per mole. That's because 1 mole of the substance is undergoing the reaction. 1 mole of CH4 is undergoing combustion. 1 mole of benzene is undergoing hydrogenation. 1 mole of sodium hydroxide is being dissolved, so it's minus 40 kilojoules per mole. The limiting enthalpy of solution, that's in as much as water molecule as possible, so it almost dilutes. So the enthalpy of ionization, that's the enthalpy change for the removal of an electron from an atom in the gaseous state. So we call that enthalpy of ionization. And then the reverse of that, the gain of electron, that's enthalpy. That's called the electron affinity. Then we have that of bond formation and bond dissociation, which is the standard enthalpy for the process in which a bond is formed or a bond is broken, respectively. So this is AB going to A plus B, so this is bond dissociation. So several other atomization, when separation of all the atoms in the substance, and then you can have so in this case atomization, so this goes into its substance. Atomization for monoatomic molecules, everything goes into the gaseous state. So we can have that of neutralization. There's something that I want to point out in this neutralization, that's the heat released when 1 mole of water. The definition of neutralization is the formation of water from an acid and a base. So the enthalpy of neutralization is when 1 mole of water is formed from a strong alkali and a strong acid. So you see, as long as it's strong base and strong acid, the energy of enthalpy of neutralization is constant. Okay, so those are just different forms of enthalpy. The most important enthalpy that we will ever come across is called the enthalpy of formation. The enthalpy of formation, the standard enthalpy of formation of a substance is the standard enthalpy of reaction of the formation of that substance from its elements in their reference states. Reference state, element. So what is the reference state? The reference state of any element is its most stable form at a specified temperature and 1 bar. It is different from the standard state, which is the state in which it is at any temperature at 1 bar. But we're talking about the most stable form at a specified temperature. So for example, if we look at hydrogen gas, the reference state of hydrogen gas is hydrogen gas. Liquid hydrogen is not a reference state. It's not the most stable form at regular temperature. Neither is solid hydrogen, and neither is the atomic hydrogen, as in ordinary H. For mercury, we have liquid mercury. The reference for oxygen, it's O2 gas. So we're looking at reference state of an element. We refer to the reference state of an element, not the reference state of the molecule. So the reason is that the standard state of any formation form, the most stable form of any element, is 0, because that is the most stable form and there's no need to look for formation of it. So we write it as the delta H of formation for C graphite is 0. Delta H, because that is its reference state. For carbon, the reference state of carbon has several forms, and one of the forms is diamond graphite, and the most stable form is graphite. Allotropes, yes, that's the word I'm trying to remember. Okay, so for example, if we were to look at this, the standard enthalpy of formation of ethanol. Ethanol is made up of carbon, hydrogen, oxygen, and hydrogen. So the two carbon in its reference state is carbon graphite. So we have 2C to make up for the 2 there. Hydrogen, there are 1, 2, 3, 4, 5, 6 atoms of hydrogen in ethanol. So we have H2. To make it up to 6, we multiply it by 3. Oxygen, we have just 1 atom of oxygen. So oxygen in its reference state is O2, and we have it as half O2 to make it 1. So this is the standard enthalpy for this reaction. So HC2H ethanol is now being formed from its reference element. The standard enthalpy for this reaction is now the delta H of formation. That's the enthalpy change of formation of ethanol. If we consider that of water, water is made up of 2 hydrogen atoms and 1 hydrogen atom. So the enthalpy of formation of water at this temperature is 285 kilojoules per mole. And for ethane, so all these are in your notes, and for ethane, we also have this. So if you just note it, so if this was a carbon, so the solid here means because carbon solid S here, graphite is also solid. So there are different, there's so many of them that have been calculated and tabulated. Say CS graphite is 0.0, for that of diamond, which is not its reference state, for carbon is 1.85. So it's important to specify the states. So for water, that's we just looked at, and then for peroxide. Anyway, now so the important thing about is that the enthalpy of a reaction can be calculated from the enthalpy of formation of the species involved in that reaction, and it will simply be the enthalpy of formation of products minus that's the enthalpy of formation of reactants. Because enthalpy is an extensive property, it depends on the amount. So you would multiply the enthalpy of formation by the number of moles used in the reaction. Okay, let's look at an example. Use the standard enthalpies of formation to calculate the delta H for the reaction. So from the tables, we have the delta H of formation of all the species. This is for CO, for CO2, and for half O2, that's 0. So using that reaction, delta H of reaction is this for the products minus that of the reactants. So we have 2 of CO2 minus 2 of CO and half of that. So if we slot in our values, we have 393 times 2 minus that. And so we have calculated, with that we calculate the